Problem 6 gives us our first kinematics equations problem. So it asks us to find the speed of a ball thrown off of a cliff 100 meters high with a speed and the x direction of 10 meters per second. So in this situation, given this is our first time using kinematics equations, I wrote all 4 of the kinematics equations out over here. I would say this is the first and most important kinematics equation that you could use. For the most part, you can do a lot of these problems with just that one. It's just position equals some initial position plus your initial speed times time plus 1/2 acceleration in that direction times time squared. The second is just velocity equals some starting velocity plus acceleration times time. And then these 2 last ones are less commonly used, but still important to have memorized. It's also important to be able to derive these. I'll make a separate video on that some other time if you need to learn that, but it's a good skill to have. So that being said, the first thing that we need to do is to start with our x direction. So we need to know both the x direction final speed and y direction final speed to be able to discover the directional speed into the ground. So so if we're just looking for speed, we can start with velocity in the x direction equals velocity starting in the x direction plus acceleration in the x direction times time. It's worth noting that there is no acceleration in the x direction because we are assuming that there is no air resistance. That means if something is thrown with a starting horizontal speed in any kinematics free-for-all projectile problem, that the velocity final will still equal the velocity initial, which in this case is 10 meters per second. Next, we want to find the final velocity in the y direction. Now, we don't have too much information, so a good place to start, if we don't have like time or anything like that, is this third equation. Because we're looking for final speed, we have an initial speed, we have an acceleration, and we have a distance, change in distance. So if we're looking for velocity in the y direction final squared, it's going to equal velocity in the y direction initial squared plus 2 times acceleration in the y direction, which is g, times the distance traveled, which in this case is going to be 100 meters. Our initial velocity in the y direction is 0, so our velocity in the y direction final is going to equal to square root 2 times g times 100. I'm going to assume, we can add this to our assumptions, that g is equal to negative 10 meters per second squared. It's a good assumption just to use 10 in kinematics problems, to use negative 10 because it's directional. If you don't, then you can plug in 9.8 if you'd like, but it's just going to lead to more difficult math. So just state the assumption clearly. I'm going to use 10 as my value. If they have a problem with that, they'll stop and correct you, but it makes the math easier. And as long as you understand it's a rounded estimation, that your interviewers will be okay with that as well. So that leads us to have 20 times 100, which is going to be 2,000. And then if we want to simplify this is going to be let's pull out 400 times 5. So we can then do 20 times the square root of 5. And this is going to be, there we go, and there's the answer. So now we have a final speed in the y direction and a final speed in the x direction. If it's worth noting from this point, we can also find time in flight, which can be relevant. You will just simply plug back into, in this case, this equation right here, because we are not dealing with position necessarily. So our v final equals v original plus acceleration times time. So we have 20 times square root 5 equals 0 plus g times time. So we know that time is going to equal 20 square root 5 divided by 10. This is a negative direction, and this is negative acceleration. So time is going to become positive, and you're going to get 10 square root 5. I'm sorry, 2 square root 5 seconds. Before we continue, I just want to correct something real quick. So when you take the square root of this is going to be plus or minus. And again, plus or minus, and we end up knowing that it's minus because our negative direction is downwards. It's worth noting that. This g in here is negative 10, and technically our starting distance, this 100 is technically negative 100. So that's why we don't have any negatives on the inside. Kind of just glazed over that and just made the assumption that you guys knew that this would be a negative at the end. But this is plus or minus, and we know it's going to be negative in this situation because our speed is bringing us downwards. But it's important to keep that g negative at certain other points in the equations because it is an acceleration that's bringing us down in our reference frame. Okay, continuing on. Okay, from here we have both of our final speeds. We know that Vy final equals negative 20 times square root of 5, and then Vx final equals 10 meters per second. So if we're looking for total final speed on impact, our V final is going to equal the square root of 10 squared plus negative 20 square root 5 squared. So this is going to equal 100 plus 20 squared times 5. And this is going to be the square root of 100 plus 400 times 5, which gives us 2100. So our final speed, if you plug that into a calculator, equals 45.83 meters per second approximately. Part B of this problem is asking us to find out if we throw the ball at a different angle, will the final speed be changed? And so there's actually a second way of solving the first part of this problem too that will be able to give us this final answer. So if we go part B, we can use conservation of energy instead. So U initial plus K initial equals U final plus K final plus whatever work might be done in the system. We know that there is no work done in the system based on our own assumptions and the fact that no energy has been added or left the system, and there's no air resistance or anything like that. Second off, there will be a U initial, so mgh initial, plus a starting velocity. So for conservation of energy, the value going into the kinetic energy is total velocity, right? It's non-directional. So this value is 1/2 mv initial squared. And in this case, the angle does not matter. It's simply the magnitude of velocity. So if we throw it at 45 degrees straight out or straight down, that value is still going to be 10 meters per second. Our final height is 0, so this is going to be the second component. The second potential energy is going to go to 0. And then we're looking for final velocity. We will have a final velocity. So 1/2 m final velocity squared. So then from here we can solve that. We can just solve for Vf squared is going to equal, first off, let's simplify this a little bit. Getting ahead of myself. We can cancel out all of these m's. Next, now we'll solve for Vf squared, which is going to multiply 2 out to the other side of the equation. and we'll get 2gh plus vi squared. And we can simplify from here. V final is going to be the square root of 2 times 10. This is going to be a positive 10 because, again, this is non-directional. It's just the magnitude times our height of 100 plus 100, which is our initial velocity in any direction, squared. And this is all to the 1/2. We can simplify this equation, and we're going to get 2100 to the 1/2, which is the exact same V of F equals 45.83 meters per second. So when you do this problem using conservation of energy, which is a little bit simpler, but I just wanted to do it via kinematics first, there, as you can see, there's no place for angles in this problem. So the initial, as long as that initial velocity is the same and the initial height is the same, the final velocity output is going to be the exact same. The angle at which it hits the ground might change, though.